Jess is going to introduce himself.
All right. Okay, so yes, I'd like to dedicate this talk to Phil Scott. So I was an undergrad at the University of Ottawa. I kid you not, Phil probably taught me half of my undergrad and also taught me how to do a math proof and put me on the path of category theory. And then, of course, he became a friend and always interested. And he was interested in differential categories. He even approached myself, Robin, and some of our other colleagues to host a special issue on differential categories only a couple months before he passed away. So unfortunately, he won't see the final results of that. But so I'd like to dedicate this talk. And for anyone who goes to CT and other conferences, you'll also see me dedicate all my other talks to Phil this summer. So yeah. So yes, so today I'm talking about an ultrametric for Cartesian differential categories, in particular to make Taylor series converge. So first, a shout out to Qualog, which was a workshop at LIX 2023, where I presented this work. And so now it's at MFPS, so I'm really happy. Okay, so Cartesian differential categories, well, sort of as the names would suggest, they provide the categorical foundations for multivariable differential calculus over Euclidean spaces. And they've been quite successful in formalizing various concepts from differential calculus. So you can solve differential equations, talk about Jacobians, gradients, etc. And then Cartesian closed differential categories provide the categorical semantics of the differential lambda calculus, as well as the resource calculus, if you know what that is. And Cartesian closed differential categories have been quite popular in computer science. In particular, they've seen a rise in popularity because they provide the categorical framework for differential programming languages and some automatic differentiation algorithms. And for those of you that do linear logic, the connection here is that the Koch-Kleisley category of a categorical model of differential linear logic is a Cartesian closed differential category. Now, of course, an all-important concept in differential calculus is the notion of Taylor series, right? So if I give you a sort of smooth real function, its Taylor series at 0, also called a Maclaurin series, is the power series where you take the sum of all the higher order derivatives of the function, evaluate at 0, where then multiplied by 1 over k factorial. And Taylor series are very useful because they actually give you lots of information about the function. And it's always highly desirable to have a function either for its Taylor series to converge, and not only that, for the function itself to be equal to its Taylor series. Now, on the other side of things, the notion of Taylor expansion is an all-important concept also for the differential lambda calculus. And so the idea here is that in the presence of infinite countable sums, one can give the full Taylor expansion of lambda terms. And so Manzanetto provides the categorical interpretation of this in a Cartesian closed differential category with infinite sums. And then this notion of Taylor series expansion for Koch-Kleisley maps in models of differential linear logic was first studied by Thomas Hérat, but also was studied by myself and my co-author Marie Cargin in our LIX paper last year, and was crucial for defining the notion of co-digging in differential linear logic. So while there's a notion of Taylor series for the differential lambda calculus, and it's morally the same thing as the notion of Taylor series in classical differential calculus, there's a slight mismatch. In the lambda calculus, you assume that you have algebraic infinite sums, right? So you can just sum up to as many terms if you want. However, infinite sums usually clashes with the notion that we learn in analysis, right? It's not that you have always infinite sums, it's that there's a metric that makes that sum converge, that makes it well-defined. So, and because of that, there are some important examples of Cartesian differential categories that don't have algebraic infinite sums like you do for the differential lambda calculus, but still have a well-defined notion of Taylor series convergence. So the objective of my MFPS paper was to provide a formal theory of Taylor series in an arbitrary Cartesian differential category in such a way that it unifies both of these approaches to Taylor series expansion. So to do so, the first thing we're going to go through together is that where you have to formalize the notion of Taylor polynomials in a Cartesian differential category. So I have to generalize this formula, which now doesn't go to infinity, but only goes up to n. So it's a polynomial this time and not a power series. And I have to generalize this formula in a Cartesian differential category. And then what I'm going to do is I'm going to show that every Cartesian differential category canonically comes equipped with an ultra pseudometric. So that's a big word. And the way that this is defined is that it's going to compare these Taylor polynomials of maps. And then I'll say that a Cartesian differential category is Taylor if that pseudometric is actually a metric. And this amounts to saying, this amounts to saying that maps are completely determined by their Taylor polynomials. And therefore, the main result of the paper is that in a Taylor Cartesian differential category, or a Taylor CDC, every sequence of Taylor polynomials converges to the function f, and therefore every map is equal to its Taylor series. And so this is not this doesn't come out of the blue. It turns out that this ultrametric is in fact the same ultrametric that we use in algebra for power series, right? There is a metric on the ring of power series that makes the infinite sums converge with respect to that metric. So this is inspired by that. And another thing, and then I show that, well, the notions that we used in differential linear logic are captured by this Taylor CDC when we look at it in the Coe-Kleisli category of differential linear logic. And I also show that this approach is the same in the closed case to Manzanetto's approach of his notion, what he called modeling Taylor series expansion of lambda terms in the closed setting. Okay, so let's start off by a quick revision of a quick brief summary of the definition of a Cartesian differential category. So we're going to fix a base commutative semi-ring K, and then a Cartesian differential category, which I'll probably just call a CDC, is in particular a category with finite products, such that each Hom set is a K module, but only pre-composition preserves the K linear structure. And the thing that makes it a differential category is that it comes equipped with a differential combinator, which essentially picks up any map from A to B and spits out its derivative, d of f, which is a map of type A times A to B. And this derivative, and d of f is called the derivative of f, and this differential combinator has to satisfy 7 axioms, which capture the basics of the derivative from differential calculus, such as the chain rule, the sum of derivatives is the derivative of the sum, etc. And there's a very practical, which is term logic for CDCs, and which I'll write the derivative, which I'll write like so. So you think of this as A is the point argument of your derivative, and B is the linear vector argument of your derivative. So what are some examples that we're going to use? So these are the two main examples. So one of them is that you take the Levier theory of polynomials for any commutative semi-ring. And so this will be a Cartesian differential category where the differential combinator is given by just the ordinary differentiation of polynomials. The other example is just instead of polynomials, we just take real smooth functions. So this time you take the Levier theory of real smooth functions, and the differential combinator is given by what's called the total derivative of a smooth function. And you can describe it as taking the total derivative of smooth function capital F is defined as the Jacobian of f, which remember is this giant matrix with all the partial derivatives of each component of big F, evaluated at x times y seen as a matrix vector in the appropriate sense. And this amounts to, in both of these formulas, you'll realize that they're very similar because R poly, so real polynomials, is a sub-Cartesian differential category of this example. Okay, so now, as I said a few slides ago, I want to express the notion of Taylor polynomials in a Cartesian differential category. So I need to generalize this formula. And so for this, there's a few ingredients that we're going to need. I'm going to need the notion of higher order derivatives. I'm going to need to be able to divide by 1 over n factorial. I need the notion of evaluating at 0. I need the ability to multiply, to have multiplication and the ability to copy input variables, so I can do x to the n, and I need finite sums. So let's first tackle higher order derivatives. So in a Cartesian, in a CDC, we can apply the differential operator n times, right? And this will give me, so if I go a to b, then I get a to b, then I get 4 copies of a. If I do it 2 times, et cetera, et cetera. So I get something where a to the power 2 to the n to b. And this is called the nth total derivative of f. However, if you look at the axioms of a Cartesian differential category, you'll realize that actually there's a lot of redundant information in the higher order total derivatives. So for example, d2, you can write out as so. And I realize there's a typo. This second d should not be d2f, it should just be df, right? Because it makes no sense what I have there. But the point is that there is a sum n of the first order of the derivative of order 1 in the derivative of order 2. So there's repetitive information there. So instead, all you really need to do is differentiate the first argument repeatedly. You don't need to differentiate both arguments in the higher order derivatives. And so for that, to make this notion precise, we have to talk about partial derivatives in a CDC. So in a CDC, we'd like to be able to take a function, say of type c times a to b, and we want to differentiate in c while keeping a constant. So I want to be able to get a map of type c times a to c because I'm differentiating c. And the way you do that is you take the total derivative of g and you just evaluate in the 0 part of, you put a 0 in there where the a is missing. And this is the exact same thing that you do in normal differential calculus. And so in this case, if you keep taking the first order, the derivative of the first argument, you don't have sort of this explosion of the dimension of your input. You only, after the nth derivative in this case will now be of type a to the power n plus 1 to b. So more manageable. So here's how you define it inductively. So we say that the nth derivative of a map f is the map of type a times a to the n to b, which I'll use this notation here. So I'm using, so the reason we have a point, so the way you think about this is that the first argument is the point argument, and the other ones are going to be the n vector arguments in your input. And you define this inductively as follows. So the 0 order derivative is just f. And then the n plus 1 higher order derivative is the derivative in the first argument of the nth order derivative. Okay, so we got higher order derivatives. Yay. Okay, so now the next thing that we need to do is we can actually knock off a few of these right away. So for finite sums, that's easy because I said that my hum sets were k modules, so I can take finite sums. Awesome. Evaluating at 0, it's the same thing. I have a 0 map because my hum sets are k modules, and therefore I can evaluate at the 0 map. There's a typo, sorry, because it's sort of spoiling the punchline. So technically, for my commutative ring k, I should be able to multiply not by p over q, but by r. I should scalar multiply my functions by r of f. What about scalar multiplying? Well, to do that, it's pretty simple. All you need to assume is that you have a 1 over n in your semi-ring, in your base semi-ring. So from now on, for the rest of the talk, I'm going to assume that k is a positive rational algebra, which essentially means that all my 1 plus 1 plus da 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 are all units or invertible in my semi-ring k. So I can scalar multiply by positive rationals. Okay, so almost there. So what about copying input variables? Well, I'm in a category of finite products, so I can just copy my input variables. Great. So the last thing we need to talk about is multiplication. So the definition of a Cartesian differential category does not assume that we can multiply maps together. Of course, in both of our examples that I gave you, polynomials and smooth functions, I can multiply, there's a notion of multiplying those maps together. However, there are examples of Cartesian differential categories where you can't do this. For example, we have a Cartesian differential category of just linear maps. You can't multiply two linear maps to get a linear map. It doesn't work. So is this going to be a problem? Well, if it was, I wouldn't really have a story to tell today. So the answer is no, this isn't a problem. The solution comes from higher order derivatives. The multiplication is hidden in there. So the way that we're going to solve this is that if you look in the example where you take just a smooth function from R to R and you look at the nth higher order derivative of that function, the last n terms are getting multiplied together. And this is the concept that we're going to use to sort of get around the need of asking for a category to have multiplication. So now we have got everything to properly define the notion of a Taylor polynomial in a CDC. So here's the definition. So the first thing I actually do is give you a Taylor monomial. So the nth Taylor monomial of a map from A to B is also the map from A to B given by taking 1 over n factorial of the nth derivative of f, evaluated at 0 in the point argument, and then copied your input variable x in the last n arguments. And this is what I'm thinking of, x to the n here. And then your Taylor polynomial is I'm taking the sum over all Taylor monomials. Now, I should explain why did I call these D polynomials, or why am I putting D here? A differential combinator structure. A category can have multiple differential combinators. So there could be different kinds of Taylor monomials depending on what derivative you're using. Okay, but another reason, is polynomial really the right word? So if I were to ask probably any undergrad student, what is a polynomial? They'd tell me it's a sum of things where you've multiplied x together and yada yada. But again, in a Cartesian differential category, we don't have the notion of multiplication. But yet there's another way to talk about polynomials, and it's the functions that after you derive n times, you get to 0. And you can talk about that in a CDC. So you can say that a map is a D polynomial if after its nth derivative, it gets equal to 0. And one can show that the Taylor monomials and the Taylor polynomials that I defined on the previous slide are in fact D polynomials. So the terminology is justified. And just as a quick remark, yes, in our examples, Taylor polynomials and D polynomials do coincide, but sometimes there are examples where they don't. Okay, so now that I have my notion of Taylor polynomials and Taylor monomials, I want to have that this infinite sum converges in an appropriate way. So now I'm going to define that ultrametric that I promised. And the way we do that is by comparing the monomials of maps. But in fact, we're first only going to define a pseudo-metric. And I'll explain what that means in the next slide. So an ultra-pseudo-metric is a map of a set M down to the positive reals, such that, well, the distance, and we think of D as distance, the distance between x and itself is equal to 0. It's a metric, and it satisfies this strong triangle and inequality. This is what makes it an ultra pseudometric. That's where the ultra comes in. And so for any CDC, I can define an ultra pseudometric on my offsets by defining the distance between two maps f and g as 2 to the minus n, where n is the smallest natural number where the Taylor monomials of f and g are not equal. So it's the first time where their Taylor series become different. And it's going to be equal to 0 if all their Taylor monomials are equal, or in another case, if their Taylor series are equal. And this makes any CDC, and this is an ultra pseudometric, and in fact, this doesn't give you say that every CDC is enriched over ultra pseudometrics. But it's important to note that for ultra pseudometrics, the distance, even if the distance between 2 points is equal to 0, x may not equal to y. And so for that, in the case where it is true, we call that an ultrametric, where if the distance is equal to 0, then x equals y. This canonical ultra pseudometric that I defined on the previous slide is in general not a metric. There can be maps whose distance is equal to 0, So that means that they have the same Taylor polynomials, but still be not equal to each other. This becomes a metric precisely when maps are completely determined by their Taylor polynomials. So, as I said in the sort of the intro slides, a Taylor Cartesian differential category is one where if for every parallel map f and g, if all Taylor monomials of these maps are equal to each other, then f equals g. And in this case, a CDC is Taylor if and only if D is an ultrametric. And again, for Taylor CDC, this becomes an enrichment over ultrametric spaces. And so the main result is that in a Taylor CDC, with respect to that ultrametric, functions converge. The Taylor series converge to their functions, which is the result we wanted. So the Levere theory of polynomials is Taylor because polynomial functions are completely determined by polynomials. Smooth functions are not Taylor, right? There are some famous smooth examples of smooth functions that have the same Taylor series, but are definitely not equal. However, if you take the subcategory of real entire functions, then this is a Taylor CDC. So just so we can keep on track, I'll go slightly faster in these last slides. But essentially, even though you start with an ultra pseudometric, there's always a way to build a Taylor CDC by doing the thing that people in metric theory do. They take a pseudometric, they do some quotienting to obtain a metric space. And the same thing works here. And this works because you have an enrichment over pseudometric spaces, doing this quotient thing preserves all the structure that you want. And so you end up getting a Taylor CDC whose Hom sets are the quotients of these things. So what about other ways that my Taylor series can converge? So I gave you two at the start. Either it can converge via another kind of metric, or it converges via algebraic infinite sums. So very quickly, what happens if I have another metric for which my Taylor series converges? Well, that's not a problem. If said other metric behaves well with the Cartesian differential structure, then it works. If your Taylor series converges with respect to that metric, then it will also converge with respect to the canonical ultrametric. However, the converse is not true. Even if I have I can have a Taylor CDC with a metric for which the Taylor series doesn't converge with respect to that metric. Don't panic. The chair told me not to panic. Okay, so what if we're in a setting with infinite sums? In the algebraic sense, so I can just take out infinite sums usually. Well, we can always take the sum of my Taylor monomials that I defined and just say, now that I have infinite sums in my Hom sets, here's the Taylor series of a map. And it's not straightforward, but someone had a really good sense. Well, it's not difficult to show that if you have countable infinite sums, then your CDC is Taylor if and only if every map F is equal to this Taylor series with the algebraic infinite sum. So for now, our ultrametric behaves well with all the other possibilities of convergence. As I mentioned, Manzanetto had his own notion, had previously defined the notion of Taylor series convergence in a Cartesian closed differential category. And he defined this, and he called this, he said that a Cartesian closed differential category modeled Taylor expansion if it had infinite sums, and sort of this evaluation could be evaluating f at a map G is equal to this infinite sum here, this sort of Taylor series expansion of the lambda terms. And again, the main result of the last section of the paper is to show that a Cartesian closed differential category with infinite sums is Taylor if and only if it models Taylor expansion in the Manzanetto sense. And so this is my last technical slide. As I mentioned, Marie-Claire Jean and I did study Taylor series expansion in categorical models of differential linear logic. And since the Koch-Lisle category of a Cartesian differential, since the Koch-Lisle category of a model of differential linear logic is a CDC, I do show that we do recapture what Marie and I did in that paper when we look at the example of Co-Kleisli maps. And in this case, the combinators M and T are actually given by natural transformations. And again, this was crucial for defining the notion of co-digging or co-promotion in a model of differential linear logic. And so, yeah, so this is my first time being in Oxford since I graduated a few years ago. So here's a picture of my probably second week at Oxford, where we did Oktoberfest at my college. So thanks for listening, and merci.
We have time for some quick questions. Whoa.
Okay.
The nearest, yes.
So realize very minimal assumptions on C, Taylor series, and then you can series
I think you do. I don't see why there should be a problem at all. My short answer is yes, but of course I didn't look at it, but I don't see why that would be a problem. I think everything's interesting, so I don't. What? Okay, so to answer to question one, we do have a higher order Taylor series, I mean a higher variable Taylor series, because in my slides, I only gave the R to R example, but my maps here are maps from Rn to Rm. So the Taylor series that you get from the Cartesian differential point of view does give you the multivariable Taylor series. So that the answer to your first question is yes, I have those. I just didn't show them for simplicity. The second point, in a Cartesian differential category, I doubt that you can capture the pole example. However, Robin, Jeff Crotwell, and Jonathan Gallagher have a notion of differential restriction categories where you can probably do that with the idea that you can zoom in on places where you're defined here, you're defined there, and so on and so forth. But I doubt you can do this in a Cartesian differential category.
Well, we should thank the speaker.
You can do it. I want the we should they should be able to join there.
they should be. Yeah, I saw them in the cool. So. Just